Welcome back. In this video, we'll look at the discoveries of radiation and the parts of the atom, and then look at the development of nuclear weapons. And we can learn some lessons from the process of the development of nuclear weapons. Obviously, scientific discovery can be dangerous. And when there's a danger of a potential catastrophe due to a technology, it should be managed early in the process. There's generally several decades prior to the time that technologies become lethal, when scientists know they could become lethal, and during that time, the world can establish guidelines. And even when technologies are initially mismanaged, the world can change course and manage them effectively. So the path to nuclear weapons began with the discovery of radiation and the atomic nucleus. Einstein developed the special theory of relativity in 1905, showing the huge amount of energy in matter. Then there were studies of how to manipulate the atomic nucleus in the 1930s. And in a supposed race against Hitler, actually Hitler didn't even come close, the United States spent $25 billion in today's money to construct a nuclear weapon. And US and Russia were at odds after World War II, which led to a huge buildup of nuclear weapons, first on the US side, then on the Soviet side. And also the development of fusion bombs, which are, I think, 1,000 times more powerful than nuclear atomic fission bombs. But the good news is that since 1987, treaties have reduced nuclear stockpiles. Well, the discovery of radiation began with some work on a cathode ray tube by the scientist William Röntgen, and he actually produced X-rays, which are electromagnetic high-energy radiation, and he placed his wife's hand over the rays coming out of the cathode ray tube and put a photographic plate behind it, and so this is her hand. They didn't realize that radiation was dangerous at the time. So there's three types of harmful nuclear radiation, and that's called ionizing radiation, which means it's harmful to the human body because it can knock an electron from atoms and cells. So there's alpha radiation, beta radiation, and gamma radiation. Alpha radiation is the emission of a helium nucleus, and that's also called an alpha particle. And it's emitted during nuclear explosions and also emitted by radium and plutonium. Beta radiation is the emission of an electron, and that's emitted by radioactive fallout. And gamma radiation is electromagnetic radiation, just like light, but it's high energy, like X-rays. And it's due to the decay of atomic nuclei between high and low energy states. So here's a cathode ray tube where they bend a beam of electrons with a magnet. And J.J. Thomson found, this is after the studies by Röntgen, that he could diffract the beam with a magnetic field. And based on the angle of diffraction, he realized the electron that was diffracted was very light. And so this indicated to him that there were electrons inside atoms and that the atom is not indivisible as they had thought in the 19th century. Then Ernest Rutherford discovered the nucleus by passing alpha particles through gold foil. So after Thomson discovered the electron, they thought the electrons were just distributed in sort of an empty space. But Rutherford noticed that alpha particles moving through gold foil, 1 out of every 7,000 particles was deflected or diffracted, which indicated that there was a very heavy nucleus at the center. So the Rutherford model of the atom was some positive charges in a dense nucleus in the center of the atom, surrounded by electrons. Think along came the special theory of relativity, where energy equals the mass times the speed of light squared. You can see the speed of light squared is a huge number. And if you just run the calculations, 1 kilogram of matter has 20 million tons of TNT energy in it. So it's huge, huge amount of energy. So based on the special theory of relativity, um, scientists knew during World War I that their work on the atomic nucleus could release a huge amount of energy. And Rutherford said that he hoped scientists would not learn how to extract atomic energy until man was living at peace with his neighbors. The discovery of nuclear fission was, in fact, made just 2 years after his death, right at the beginning of World War II, of course. And so that's why they thought that they needed, both sides thought that they needed to develop nuclear weapons as fast as possible so they'd be the first. So anyway, that happened right at a time that Rutherford had said would be catastrophic. But the interesting thing is, and we can't really criticize him because this kind of thing had not happened before, that there was a technology that would be harmful to the world. The interesting thing is they didn't do anything to regulate it. They just let the research keep going. And, you know, it was kind of a crapshoot. It might have been nice if they discovered it in the 1925 when there was no war or something like that, where maybe they could have given the technology to the United Nations, but it didn't happen that way. And you just can't take chances like that anymore. At the end of this lecture, I'll talk about several technologies that need to be regulated. So in the 30s, Rutherford bombarded the nucleus with alpha particles and noticed that the properties were changed because the nucleus absorbed the alpha particles. So they began to find out that they could change the nucleus. Also during the early 30s, they found that there were neutrons and protons in the nucleus. It wasn't just protons. So they were making progress towards understanding the nucleus. And then Pierre and Irene Joliot-Curie, and I forgot to mention that Marie Curie, in the late 19th century, discovered alpha particles. And there was another person, Becquerel, I think he might have discovered beta particles. But they, you know, those were not from a cathode ray tube, but from Marie Curie used uranium salts. And so this is her daughter, actually, Irene Joliot-Curie. And so she's using alpha particles to make non-radioactive elements radioactive. So she's destabilizing them. And then in 1934, Enrico Fermi, an Italian physicist, bombarded uranium with slow neutrons and formed seemingly new elements. And Ida Nodak, who was another scientist at the time, proposed that Fermi's new elements were caused by nuclear fission, and the uranium nucleus had been divided. And it's fortunate that people ignored her. It sounded a bit unreasonable, you know, that you could divide an element. But actually, that's what happened. She was right. But it's probably fortunate, I guess, from our perspective, that Italy, later Germany, was not alerted to the technology earlier. So the research continued, and Hahn, Meitner, and Strassmann conducted an experiment in Germany where they slowed down neutrons in this paraffin wax. And so then they bombarded uranium with neutrons. And at that time, Meitner, who was a Jew, had to flee Germany because of the persecution of the Jews. Even though she was actually a Christian, she was culturally and by ancestry a Jew. So she left Germany. And so Hahn was left with the experiment. And so again, they found that by bombarding the uranium nucleus with slow neutrons, they were forming actually barium and krypton. So they were quite amazed by that. They really couldn't believe it was true. But Hahn wrote to Meitner, who was in Holland, "Perhaps you can suggest some fantastic explanation. We understood that it really can't break up into barium. So try to think of some other possibility. Barium isotopes with much higher atomic weights than 137. Then Meitner wrote back, "Your results are amazing. A process that works with slow neutrons and leads to barium. To me, for the time being, the hypothesis of such an extensive burst seems very difficult to accept. But we experience so many surprises in nuclear physics that one cannot say without hesitation about anything. It's impossible." then the problem was, it wouldn't have been a problem, but this reaction of bombarding a uranium nucleus with a neutron, or yeah, a neutron, so neutron, produces 3 more neutrons, which indicates that this could be an explosion, because obviously that this would be a chain reaction. And Leo Szilard and colleagues found that excess neutrons, they found this, were produced during nuclear fission, which confirmed that a nuclear bomb was possible. And he urged his colleagues not to publish the paper because it would lead to a nuclear arms race, but they published the paper anyway in 1939, and the nuclear arms race was on. So Einstein wrote Roosevelt and told him of the need for America to develop nuclear weapons. And then in Germany, they started the Nuclear Club, where several scientists were responsible for developing the nuclear bomb for Germany. So the United States developed the Manhattan Project from 1942 to 1946. There was 130,000 people involved, mostly involved in enriching uranium, but many scientists as well. As I said before, they spent $25 billion in modern dollars. 90% of the funds spent were for separation of or enrichment of uranium, and they made a uranium bomb and a plutonium bomb. So here are some centrifuges which they use to separate U-235 from U-238. Natural uranium is mostly U-238, but to make a bomb, they need a high concentration of U-235. So if you've probably heard of centrifuges before, like in some countries enriching uranium to make bombs. Well, that's what they're doing. They're separating out the U-238 from the U-235. The Germans actually never came close to producing an atomic bomb, and German scientists were then put on trial after World War II, and at Nuremberg, and in their trials they claimed that they intentionally did not succeed with atomic research because they did not want Hitler to have an A-bomb, so they were released. And then probably the most famous of those scientists was Karl von Weizsäcker. He became a crusader for nuclear disarmament, and he died in 2007 at age 95. So he was the last member of the German Uranium Club. So the question arises, did the US really need to bomb Hiroshima and Nagasaki? According to many people, the Japanese were ready to surrender anyway because of Russian advances in Manchuria, and they didn't want to surrender to Russia. And actually, almost all American generals advised Truman that we did not need to drop the bomb. And then the second question was, well, once we dropped the bomb, was a nuclear arms race necessary? And there's, again, a lot of controversy over whether Truman should have alienated Stalin, which he did on purpose after the war, and developed America's nuclear arsenal. Actually, during his presidency, the arsenal wasn't increased a huge amount, but it began, the research, the efforts to develop the bomb. But then Eisenhower came along and built up America's nuclear arsenal to an insane level, which is not surprising since he had a military background and that was, what you do. And then the nuclear arms race led to the development of tens of thousands of nuclear bombs and an ever-increasing number of countries becoming nuclear. So what we can do is we can look at why nuclear energy, nuclear weapons is different from the past. So in the past, military buildup by civilizations followed by war was the norm. And in the past, there were always, women and children and some remaining men to continue civilization after catastrophic wars. Not ideal, but sustainable. But once people discovered nuclear weapons, which had the capability to destroy all life on Earth, that practice of military buildup just wasn't sustainable because anybody, anytime, who's in charge of nuclear weapons, and there's 8, 10 countries in the world that have nuclear weapons, could launch enough nuclear weapons to, at least destroy the environment. So it's very scary. And here's what we have in the development of nuclear weapons. We have the US, and mostly during Eisenhower's term, building up to 30,000 nuclear weapons, and then following nuclear warheads. And then Russia followed along behind, and then this is right at the point of the fall of the Soviet Union. And then they've had treaties since then, beginning in 1987 with Reagan and I think Gorbachev, where they've reduced down to, I think it's 5,000 on each side. I'm not exactly sure. But there has been huge progress towards disarmament. According to the New START treaty, which was signed under Obama, there's supposed to be only 1550 weapons on both sides, but warheads. But I think now there's maybe 13,000 total in the world. So I'm a little confused on the numbers. But anyway, the Obama administration negotiated the New START treaty in 2010, which reduced the total number of nuclear warheads to 1550 on both sides. It was ratified by the Senate in 2011, and that treaty expires in 2021 in February, so about 6 months away. And Trump wants to replace the New START treaty with a treaty that includes China. So China is expanding its nuclear arsenal rapidly. Trump also abandoned the 1987 treaty in 2018. So New START is the only remaining treaty and expires in February 2021. So I think there's 13,000 nuclear warheads in the world at this time. Actually, the present nuclear arms race is the modernization of these weapons. And in 2008, which is a while back, at the Global Catastrophic Risk Conference, they estimated that the chance of the extinction of humanity is about 1% in this century. Chance of 1 billion dead is about 10%, and chance of 1 million dead is about 30%. So I don't know where they got their numbers, but in addition, recent studies have shown that a small-scale nuclear war, such as if India and Pakistan released 30% of their nuclear weapons, could cause a nuclear winter. So even that could be catastrophic. There's other nuclear uses. One of the advantages is that nuclear reactors produce energy that does not cause global warming. But the failures have catastrophic consequences, Chernobyl and Fukushima, for example. America also makes conventional weapons with uranium-238 in order to penetrate tank armor, which is really awful because the shells remain there, or the little missiles. And so it's very radioactive. And for example, the women in Basra are told not to have babies, and uranium has like a 4 billion year half-life. So I don't know if that's how long it will be dangerous, but that seems like a very bad idea that should be outlawed. There's many potential catastrophic technologies. I talked about this at the beginning of the lecture that need to be managed at a world level. And for example, chemical and biological weapons are managed at a world level. There's world treaties banning them. Every once in a while somebody comes up with some. I was thinking information technology could be dangerous. We've all watched the movies about computers taking over the world. I don't know, but that's something that people need to keep an eye on. Of course, atomic fission and fusion, and then combustion of fossil fuels and global warming. That's a world issue, could be catastrophic. And in the 80s, they had an ozone treaty where they banned the use of certain refrigerants which deplete the ozone layer. We'll see you next time.